You know, some of the most powerful and honestly most beautiful ideas in all of mathematics come from asking a really simple question. What if? What if we could solve a problem that everyone says is impossible? Well, today we're going to do exactly that. And in the process, we're going to discover a hidden universe of numbers you never knew existed.
All right, take a look at this. Seems simple enough, right? Your first instinct is probably to subtract 1 from both sides. That leaves you with x squared equals -1. But hang on, what number, when you multiply it by itself, gives you a -1?
See, if you're only using the numbers we all know and love, the ones on a regular number line, there's just no answer. A positive number times a positive number is positive, and a negative number times a negative is also positive. So, yeah, we've kind of hit a wall. Or have we?
What if, instead of just throwing our hands up and saying impossible, we just invented a new number, a number whose whole job is to solve this one problem? Well, that's exactly what some brilliant mathematicians did. They decided to imagine their way right through that wall. So, let me introduce you to the hero of our story, the imaginary unit, which we call I. It was literally invented for one reason: to be the number that, when you square it, you get -1. That's its entire purpose. It's the key that's going to unlock this whole thing.
And boom, just like that, our impossible problem is solved. If we say x equals I and plug it back into the equation, we get I squared plus 1. And since I squared times is -1, by its very definition, we get -1 plus 1, which is 0. It works perfectly.
But why on earth would we stop there? We can now combine our familiar real numbers with this new imaginary unit. This gives us a new kind of number with two parts, a real part a and an imaginary part bi. And together, they form a complex number. And believe me, this isn't just some abstract math game. These numbers are absolutely crucial in the real world for things like electrical engineering, digital signal processing, even quantum mechanics. This stuff is everywhere.
Okay, so if these new numbers have two distinct parts, a real part and an imaginary part, where do they actually live? You can't just stick them on a plain old number line, right? We're going to need a new kind of map, one with a whole new dimension.
And here it is. This is the complex plane. That horizontal line, that's your good old real number line. But now, check it out. We've added a vertical axis for the imaginary part. So any complex number, a plus bi, can be plotted as a unique point on this map, kind of like coordinates a, b.
So once we've plotted a point on this plane, there are a couple of cool ways to talk about where it is. First off, how far is it from the dead center, from the origin? That distance, that's what we call the modulus. It's basically the size or the magnitude of the number. Okay, so we've got the distance. What else do we need? Well, what about its direction? If you draw a line from the center out to our number, what angle does that line make with the positive real axis? That angle right there, that's the argument. It tells us which way our number is pointing.
So you see, it's just like finding a place on a real map. You could use grid coordinates, right? Like go 3 blocks east and 4 blocks north. Or you could just say, go 5 blocks in that direction. Both methods get you to the exact same spot. It's the same idea here.
And this whole distance and direction thing, it gives us an entirely new way to write our complex number, called the polar form. Now, I know, this looks way more complicated, with the cosine and sine in there, but trust me, this polar form is about to unlock a mind-blowing superpower. Because, and this is so cool, it turns out that looking at numbers this way reveals something incredible. Multiplying complex numbers is really just a simple act of rotation and scaling. And this is where the true beauty of this whole system just shines through.
So what happens when you multiply a complex number by itself, when you square it? Well, in this form, you just square the distance and you double the angle. Simple. What about cubing it? You guessed it, you cube the distance and you triple the angle. Are you starting to see the pattern here?
This incredibly elegant pattern has a name, and it's called de Moivre's theorem. It basically says, hey, forget all that messy algebra. To raise a complex number to any power n, you just raise its distance to the power of n and multiply its angle by n. It turns complicated calculation into pure, simple geometry.
Okay, so here's the crucial part. This amazing theorem doesn't just work for powers, like squaring or cubing. It also works for finding roots, which, if you think about it, are just fractional powers. And with this new tool, we can finally solve equations that were completely out of reach before.
So let's put it to the test. What are the cube roots of 1? Now, of course,
x equals 1 is an answer, duh. 1 times 1 times 1 is 1. But wait a minute. A cubic equation is supposed to have 3 solutions. So, where are the other 2?
Well, using de Moivre's theorem, we can finally hunt them down. And it turns out the other 2 solutions, they've been hiding from us this whole time. They aren't on the real number line at all. They're complex.
But this is where it gets truly mind-blowing. When you actually plot these 3 roots on our complex plane, look what happens. They form the points of a perfect, beautiful, equilateral triangle. These solutions weren't random at all. They had this incredible, perfect geometric symmetry.
And get this, the pattern doesn't stop there. The 4 fourth roots of 1, they form a perfect square. The 5 fifth roots, a perfect pentagon, and on and on. It's like we've pulled back a curtain to reveal this deep, hidden order in the universe of numbers. A structure that was there all along, just waiting for us to find the right map.
And all of this leaves us with one big, final thought. Remember how we started? With this simple little equation that seemed impossible to solve. And by daring to imagine a new number, we ended up discovering this entire hidden geometric universe. It really makes you wonder, doesn't it? What other impossible problems are out there, just waiting for someone like you to come along and imagine a new way to solve them?